that this recording is going up so late in the week. Time got away from me this week. I'll make sure that the last lecture slides are up with plenty of time. If you need some more time to complete the assignment for these slides that's due on Monday, just send me an email and let me know if that will be a problem to get them done by Monday. And, we'll make some arrangements for you to hand them in later. Okay, so today these slides are going to be focused on experimental designs and longitudinal designs. So going off of last week where we focused on internal validity and causal claims, I made reference to what experimental designs can help us to establish and understand in terms of those causal criteria. Okay, so today we're going to dive into a little bit more about an experimental design and how it can help support those causal claims, what it does that helps us get at causation, what helps us get at covariance, temporal precedence, and may help us to establish internal validity. Okay, so if you flip through your textbook, you can see that there are a lot of variations on experimental designs. They can become increasingly complex. There's a lot of manipulations that can be done. There are a lot of advanced statistical techniques that we're not going to cover today, and we're not going to cover in this class. That's really more for a statistics class. What we are going to go over, though, is really understanding what an experimental design can do, what we can learn from it, and also how it differs from these other designs that we've talked about so far. So we've talked about a correlational design. Today we're also going to touch on longitudinal designs as well. Okay, so I'm going to go through some experiments, some examples of these experiments to kind of get us thinking about what an experimental design does. So these examples are all from your textbook, so you can kind of follow along or read along there to get some more insight into how I'm describing this. So the first example here is, say that we're a researcher and we want to understand whether or not taking notes by laptop or by writing out our notes helps us to perform better on factual questions versus conceptual questions on a standardized test. Okay, so there are a couple of different variables here that we want to think about. We're going to think about the method of taking notes. We're going to think about the type of material that is being tested. And then we're going to look at the outcome, kind of the dependent variable here, which is how we perform or the score on the test. Okay. So take a second and just think about what this question means. What do we think? What would our hypothesis be about, the method that we use to take notes and how we may perform in different ways? Okay, if we look at this graph, we can actually get some information from an experiment about what they found, what kind of inferences we can make about these associations. Okay, so this graph is telling us that for students who took notes by longhand, by writing out their answers in their notes, they performed significantly better on conceptual questions on this test. Okay, students who took notes on a laptop performed significantly worse on conceptual questions. So there was a significant effect here of how notes were taken for conceptual question performance. Okay, so conceptual questions are things that require critical thinking, okay, that you have to apply. If we look at the factual questions over here, we can see that there's really no difference. Okay, I'll tell you just from looking at this that there's no significant difference between the method that students used and how they performed on factual questions. Okay, so this makes sense, right? Factual questions are things that just require us to maybe give a definition or remember something for a short period of time and kind of feed that information back. Okay, so these results are telling us that taking notes by longhand, by writing them out, may be better for these more applied kind of concepts. Okay, so the next thing that we have to think about in how an experimental design can be interpreted and can be used is what types of variables are we testing? Okay, so we've talked about measured variables and manipulated variables before. I actually have a note in the bottom of this slide as well for you to take a second and think about the manipulated variable and the measured variable in this equation. Okay, what would this experiment be manipulating and what would it be measuring? Okay, so just as a reminder, a manipulated variable is something that the experimenter controls, okay, that we go in and we make a decision about whether it's in a lab setting or it's something that people are exposed to, it's something that is, relatively controlled and determined by the experiment itself. The measured variable is something that we just observe or we have people report on. We don't go in and control it. We just kind of see what happens. Okay, so typically we think about, in the context of an experiment, the manipulated variable is the independent variable, and the measured variable is the dependent variable or the outcome. Okay, so here, the manipulated variable would be the method for taking notes. Okay, we could divide a class in half and tell half of the students randomly, assigned to take notes on a laptop, and the other half to randomly be assigned to take notes by longhand, and then see what happens. The measured variable would be their performance on the test on these different types of questions. Okay, we're not manipulating anything about how they perform, but we are manipulating what they're doing to get there. Okay, hopefully that makes sense. We'll look at another example here about eating pasta. Okay, this is also from your textbook. This example is derived to examine whether or not the size of a serving bowl has an impact on how much pasta we serve ourselves to our own plate, and that's in A. And then in part B, whether or not the size of the serving bowl has an impact on how much we eat. Okay, so some of you may have an idea here about where this is going, that if we have a larger bowl that we're serving from, we are going to give ourselves more pasta. And same thing, if we have a larger bowl that we're serving from, we may also be more inclined to eat more pasta. Okay, and that's exactly what these figures are showing here, right? In A, we can see that there is a significant difference in how much we serve based on the size of the bowl that the pasta is being served out of. And we can also see the significant difference here between the two bars in how much we consume, how much we eat based on the size of the serving bowl. Okay, so take a second here again and think about what would be the measured variable and what would be the manipulated variable in this example. Okay, so I'll tell you that in both of these examples, the independent variable or the manipulated variable would be the size of the serving bowl. Okay, you can look down here. The x-axis is always going to show, that's a little trick, I guess. If you have a graph or a figure, the x-axis shows the independent variable or the predictor, and the y-axis is going to show what's measured. So the researchers had nothing to do with how much people served themselves or how much they eventually ate. That was simply something that was measured. But they did manipulate the condition that they were exposed to, the size of the serving bowl that they were presented with. Okay, so that would be something that's manipulated. Okay, so just to sum up these terms, an experiment is any type of study design where the researcher manipulates one variable and measures another. Okay, and that's as simple as it gets in an experiment. You just have one variable that's independent, that's being controlled and manipulated, and you have an outcome or a dependent variable that you're measuring to see what happens. What was the effect? Ideally, we're going to try to determine what was the effect of whatever was manipulated. Okay, so like I mentioned before, a manipulated variable is controlled. Somebody may be assigned to a certain condition. They may be assigned to get a certain treatment, or part of a group that gets something like, a bigger pasta bowl to serve themselves out of. Okay, the measured variable is a record or a report. It's something that the participant either reports on themselves. It could be a behavior that's observed or a measure that's taken even physiologically from them. It's not something that the researcher has any control over, but it's the outcome. The researcher is looking to see what does the effect of this manipulated variable have on what people do or how they behave. Okay, so when we think about manipulated and measured variables in the context of experiments, again, it's the same term, it's the same way of thinking as when we talked about the same concept a few weeks ago. Okay, so this should be a little bit familiar to you guys. Other terminology that goes along with an experimental design, I think I mentioned this early in the semester in class. When we have an experiment, we typically refer to the predictor as the independent variable, okay, because it is independent of the outcome. Okay, this is something that's being manipulated and it's coming from an outside source in a sense. The participant themselves doesn't have anything to do with the independent variable. Okay, there are study conditions or levels that go along with the independent variable. Okay, levels don't always have to mean numbers. In the examples that I gave before, the conditions or the levels were things like the method of note taking or the size of the serving bowl for pasta. Okay, way back when we talked about variables and what it means to be a variable, we talked about levels, right? So a variable has to vary. It has to have at least two levels. There have to be, more than one determination or factor for that variable to have. So conditions in an experimental design really mean just that there has to be more than one level of variation of the independent variable that you're looking at. You have to look at more than one thing. Okay, the dependent variable is also referred to as the outcome variable or the measured variable. In a non-experimental design, that's how we talk about it, as an outcome. Researchers, again, have little control over how people respond on the dependent variable, and that's by design, right? We don't want to manipulate what they do. We want to manipulate, the independent variable to see the effect that it has. Another variable that may be introduced in an experimental design is a control variable. So this is anything that the researcher holds constant on purpose. So that's a little bit of a statistical terminology, holding constant. It basically means that you're going to factor something out or cancel it out to zero. When we hold something constant or control for it, we enter it into the equation so that the level is the same for all participants. And this allows researchers to help to separate out potential causes from one another. Okay, so when we have identified a potential confound in our experiment or in our study, we can sometimes take that confounding factor and control for it. Okay, make it a variable that we account for in the statistical equation so that it's factored out, it's zeroed out, and it's not going to necessarily have an impact on our outcome. Okay, so in the example that we talked about before with the pasta, potential confounds could be things like type of pasta, right? If everybody is not being served the same type of pasta, that could introduce some error or some variability. Maybe people are going to eat less of a certain kind of pasta because they don't like it as much, right? It has nothing to do then with the size of the serving plate, but it has to do with the fact that they're being served pesto and they really like vodka sauce, right? So you want to make sure that you keep everything controlled and similar. And if you can't, then you want to enter in a way to control for that, in maybe measuring the type of pasta and accounting for that, and then zeroing it out of the equation so that it doesn't impact your results. Okay. The size of the plate could be another confound, that if people have a big serving bowl, but they have a small plate to put their pasta on, and other people may have, a normal sized plate to put their pasta on, they're going to take a different amount of pasta, and it may not have anything to do with the serving bowl. It has to do with where they can put it, right? So that's another potential confound that we would ideally like to eliminate or at the very least control for. Okay, so a lot of times in any type of study, it doesn't have to be an experiment, we try to control for the variables that we think could potentially influence our results. Okay, so right now I'm conducting a study or I'm analyzing data where I'm looking at the associations between adolescent adjustment and co-parenting. Okay, so something that's really important for me to control for is marital quality and marital conflict. Okay, that's something that's highly related to co-parenting and to child adjustment. So I want to make sure that my results are actually showing the relationship between co-parenting and child adjustment independent of marital quality. Okay, I want to kind of factor marital quality out of that equation so I control for it. A lot of times we control for socioeconomic status, or we control for gender or race. we want to make sure that we're not seeing different patterns for those groups if we're not trying to discern different patterns for them, right? We don't want those factors to kind of override our results unless we want to know what those differences for those groups actually look like. Okay, so a lot of times we actually control for variables that we just want to kind of not take into account in influencing our outcome. Hopefully I didn't confuse you more than I helped you. But if you have questions about control variables, let me know. You can also find some more examples and more information about this in your textbook. All right, so this leads us to this next question here as to, we know what experiments do and how a simple experiment might be conducted, what the variables that it involves are. Now, how does an experiment help us support causal claims? Okay, how are we be able to say that an experimental design gives us insight into a cause and effect relationship that a correlational design doesn't? Okay, so for one, experiments do establish covariance. Okay, we are able to find an association between an independent variable and a dependent variable. Okay, it's not to say that every experiment is going to necessarily find a significant relationship, but it is designed to detect those types of associations. Experiments are also designed to establish temporal precedence. Okay, we will come back to this idea in a couple of minutes when we go through the different types of experimental designs and also when we get into longitudinal designs. But keep in mind that temporal precedence means that we have to understand that the independent variable happened before the dependent variable, right? And, reading through your assignments from last week, I think you guys are onto this idea that the cause has to happen before the effect, right? A well-designed experiment also can establish internal validity. So this is, again, the hardest part of any type of design, to be able to rule out these confounds, these additional or alternative explanations for our findings. But it's possible with a well-designed, very well-controlled experiment. The trade-off with a well-controlled experiment, just to tie this into what we learned a few weeks ago, is the trade-off to external validity. Okay, when we have something that's really well controlled, we are losing potentially some kind of real world sense. We're losing the ability to potentially generalize what we find to a situation that's not so highly controlled. All right, so experiments establish covariance. The independent variables help us answer the question about the comparison group. Okay, so when we have an experimental design, we are going to have people who are divided into two or more groups to be able to compare the effect of the treatment to, or to the effect of taking notes one way versus another. The comparison group helps us to understand who is this working for compared to who is not getting this treatment at all. All right, so again, covariance addresses this question as to whether there's an association between the two variables. Manipulating the independent variable in an experiment is necessary for establishing covariance. It allows us to determine these different comparison groups. Okay, so by manipulating the level of the independent variable, you're able to compare how and how much the outcome differs according to one level of the independent variable versus the other. Okay, and again, levels of the independent variables are the same thing as those comparison groups. Okay, you're going to have people who are at one level and people who are at another level, which is potentially the control group. You're going to have people who get the treatment and then people who don't get it at all. Leading right into the next slide. The control group is the level of the independent variable that is intended to represent no treatment. Okay, not every experiment has a control group that represents nothingness, but a lot of them do, especially when we think about a clinical trial. Okay, this is really relevant in today's climate. We want to know whether or not a certain drug works to treat a virus. So we're going to have people who are part of a treatment group who receive the drug, and people who are part of the control group who don't receive the drug, or who maybe receive a placebo drug, so they don't know if they're getting it or not. And then we want to compare between those two groups, right? This allows us to have a comparison to see if the drug worked for one group and not the other. And ideally, we would want to see that the treatment works for the treatment group and that they improve, and that the control group does not improve at all. Okay, I shouldn't say ideally, because we don't want people to not get a treatment when they need it. And that's a whole nother kind of set of questions about ethics and how that's handled. And just to give the short answer for that, a lot of times in experiments like this, people who are part of a control group will then get the treatment after they're part of the control group. So after it's been established that it works, they can kind of switch groups so that they get it. In other, kinds of experiments that have lower stakes, sometimes people participate in a parenting kind of program where they get the treatment, which is parenting classes. The control group may not be the same level of parenting classes, but they might get a workbook. So they get something. They don't necessarily get nothing, but they're not getting the level of treatment that the program is intending to test. All right, so this is a representation of a simple experimental design and how we can establish covariance. Okay, so over here you have your participants, and they're randomly assigned. Okay, these arrows represent random assignment to a treatment group, to a treatment group B, and to a control group. Okay, so sometimes you can have multiple treatment groups, or you could have one. The thing about this independent variable is that you have to have at least two levels, right? So you have to have at least one treatment group and one other group, whether it be a different treatment or a control. And then we're going to give these participants whatever it is that they are assigned to. And after that, we're going to measure them on the outcome. Okay, so everybody is just going to report or be observed on the dependent variable. All right, so I wrote in the notes down here, applying this, this figure representation to the pasta example, okay, or the handwriting notes example. Our participants would be randomly assigned to receive pasta in a really big serving bowl versus a smaller serving bowl, okay? And then we would measure them on the outcome, which is how much pasta did they consume. All right, the second point here about these causal criteria is that experiments establish temporal precedence, meaning, again, that the cause variable has to come before the effect variable in time. So in our example, the serving bowl size has to be manipulated before the pasta amount was measured. Okay, that makes sense, right? That people have to be presented with a certain size of a serving bowl before they serve themselves or eat the pasta. Okay, so that's obviously taken care of in that experiment. In most experiments, and we'll come back to this idea in a second again when we look at the different types of designs, an experiment is set up to have the independent variable be delivered before the outcome is measured. All right, well-designed experiments can establish internal validity. The biggest threats to this, that we have to be aware of, things like design confounds, selection effects, and just confounds in general can threaten internal validity, even in an experiment. All right, so design confounds are when there's a second variable that systematically varies along with the independent variable and can provide an alternative explanation for the results. Okay, so I kind of gave you a sense of what a design confound might look like in describing confounds earlier. So what if students who took notes in one format received different test questions? What if the questions for students who handwrote their notes were more difficult? Or I should say that the other way around, right? Because the handwritten notes, they perform better. If students who took notes on a laptop, if the questions that they received were more difficult, and that explains why they didn't perform quite as well on the test, rather than the fact that they took notes in a certain way. Okay, so there's a systematic variation with the treatment, right? So only students who were in that group received those tests. So it's impossible to determine whether it was the method that the notes were taken in or if it was the actual test itself that was more difficult that led to that outcome of not performing quite as well. Okay, so you can see how that provides a really big problem for how you interpret your results. Same thing with the pasta dish experiment. If people who received larger serving sizes or larger serving bowls of pasta were presented with a much more appetizing type of pasta, they may have eaten more because it tasted better, right? Or because they liked it more than maybe the other group who had a smaller serving size and they, got a really bland kind of pasta dish. So design confounds really speak to the importance of having a really well-controlled experiment. You want to make sure that everything that can be kept the same or kept controlled for these two different manipulations is done, to the best extent possible. It's also important that that randomness is kept in mind. Okay, we'll come back to this idea in a second. But when there is unsystematic variability that's random and can affect both groups in the same way, it's generally not a problem. Okay, so when something is systematic, it's a problem because we can't discern systematic variation from the groups that we have and from the outcomes that we're finding. When we have random variability that may affect both groups in a similar way, it typically doesn't really have a bearing on our outcomes, right? We expect that everybody in our class is going to have different performance on the test. Not everybody is going to get 100% because they took notes in a certain way, right? We're going to still expect to see individual variation. Not everybody is going to like the same kind of pasta to the same extent. If this is random though, and if you don't have all of the pasta lovers of one type of pasta in the group that are only getting that type, then it's typically not a problem because those random preferences are spread out among both groups and they can potentially cancel each other out. Okay, I have a figure here that can hopefully help us to understand the difference between systematic variability and unsystematic variability. Okay, so unsystematic variability is not a problem. It's not the same thing as a confound, which is systematic variability that's problematic. All right, so we can see here all of these are the different people who are participating in our pasta study. All right, so we have this person here is gluten-free. They're going to have an issue, right? This person hates pasta. This person is dieting. So we're going to expect these people maybe to not eat as much. This person didn't eat breakfast. This person loves pasta. This person likes to eat. All right, these people we're going to expect to probably eat more. Over here on this side, the people who are served from a larger bowl, same thing, right? We have a light eater, we have a vegetarian, we have a big eater. All right, so these people represent unsystematic variability. Okay, we have people with these different preferences, different backgrounds, making up both groups. And these are, characteristics of people that can potentially affect what we're looking at. It's unsystematic because they're not all part of the same group. They're not really going to have an overwhelming impact on the findings. It would be a problem, it would be a confound if all of the light eater, gluten-free, dieting people were a part of one group. Okay, and it doesn't even really matter which group, but if you have them all being a part of one group, there is an underlying factor that they share that's systematic that could actually be contributing to your results. Okay, and not to the fact that they're being served in a certain size bowl. Okay, hopefully that makes sense. I think this figure illustrates it really nicely. All right, a selection effect, we've talked about this a few times already. It means the same thing as it did last week. Basically, a selection effect is when the types of participants in one group or in one level of the independent variable are systematically different from those in the other. Okay, so we can apply a selection effect to this same example. If we let people choose which group they wanted to be a part of, we can end up with a problem, right? If we said, you can be in this experiment and you can decide if you want to have a larger bowl or a smaller bowl of pasta, who's going to go, select themselves into which group? We have an idea, right? You're going to have the pasta lovers, the big eaters, the athletes maybe choosing or selecting into the larger serving size group. Okay, so it becomes problematic when there isn't this random assignment of people, being kind of sorted into the groups that they're in. Ways that researchers can resolve this, can try to get around selection effects, are through random assignment and matched groups. All right, so random assignment is just what it sounds like. It's basically when people who are part of the sample are randomly assigned to be in one condition or the other. Okay, so flip of the coin, something really simple. Go down the list like in simple random sampling and just pick names and say, you go to this group, you go to this group. There's nothing that's decisive or underlying about the choices. And there's nothing that should be systematic in the groups that people are assigned to. Matched groups are a little bit different. In a matched group type of assignment, people's background characteristics are measured and they are grouped up with somebody who's very similar to them. And then those people who share a lot of characteristics are split into one of them goes to the control group and one of them goes to the treatment group. Okay, so this way you can kind of determine that you don't have everybody who shares similar characteristics pooled up on one side. Okay, thinking about this, it's interesting actually. I got a phone call today from my school district. So for kindergarten, my daughter will be in kindergarten in the fall as long as there is kindergarten. They do assessments of kids who are entering, who are in pre-K right now. And they look to see, kind of just where they're at on a lot of different measures of child development. They use that information to put kids into classrooms. So they go to kindergarten. I think there's something like 10 classrooms in the kindergarten center that she'll go to. And they want to make sure that kids who are all of the same ability levels aren't put into the same class, to make it better for learning, to make it better for teachers and whatnot. So they give them these assessments and then they'll take kids who, score the highest and they'll split them up among the different classes. And then they'll take the kids who score the next highest, at the next level, and they'll split them up, okay, and so on. All the way down to the bottom, the kids who score the lowest also won't be clumped up in the same class. So everybody is kind of evenly divided among classrooms. So to say, I don't know if this system is any different than if you just randomly pick names off a list and put kids in classes, but this is how they do it, and it is a way to kind of get around selection. Okay, so that's another example for matched groups. All right, so a couple of different experimental designs that we're going to talk about. There are independent group designs that are different from within group designs, post-test only designs, and then there are pre-test, post-test designs. All right, so independent group and within group designs are kind of the umbrella for these other types that we're going to talk about. An independent group design is also called a between subjects design. So basically what we've been talking about so far is an independent group design where each participant is randomly assigned to one condition. Okay, so you're chosen to be in my study. You're either going to take notes by hand or you're going to take notes on a laptop, and that's it. I'm just going to compare the group then, the people who took notes by hand to the people who took notes on a laptop, and then my study will be over. All right, with a within groups design, I'm going to give all of the participants in my sample an opportunity to be a part of each group. Okay, not at the same time, but I'm going to do my study maybe over and over. And those participants are going to get a chance to be in the treatment group, and then maybe they're going to have a chance to be in the control group, or they're going to receive a different treatment. All right, in a post-test only design, I'm going to look at the simple association between what people are exposed to in the independent variable and how they score on the outcome or on the dependent variable. Okay, so very similar to the example that I showed in the beginning of these slides, the first figure that I showed about an experiment. So I'm going to randomly assign my participants. Okay, I'm going to randomly assign them to either take notes by hand or on a laptop, and then I'm going to measure them on the dependent variable on their performance on the test. All right, and then that's it. I'm only going to take one measure of how they performed after I have divided them into these two different groups. A pre-test, post-test design is a little bit longer, a little bit more complicated. It allows us to establish a baseline for what we're trying to measure as an outcome. Okay, so all I'm going to do differently in a pre-test, post-test design is gain a baseline measure of performance on the outcome variable before I expose people to the independent variable. Okay, so again, I'll start off with randomly assigning people to one of these two groups, okay, independent variable, or I should say treatment group or control group. And then I'm going to collect information about how they score on the outcome before I do anything. So in this example, I'm going to maybe get their verbal GRE scores. Okay. The treatment is the type of class that they take. So the students who are part of this treatment are going to take a mindfulness class, whereas these students are going to take a nutrition class. And then we're going to look to measure the outcome again, the dependent variable again, after they've been exposed to the independent variable, to see both how much they change from before and also how different they are compared to each other. Okay, so those are the two pieces of information that we get from a pre-test, post-test design. We can see from before you had this type of class, how much better did you do on the verbal GRE? The students who took the mindfulness class, were they more able to focus? The students who took the nutrition class, did that benefit them in some way? Okay, so we can make this comparison. We can also make the comparison to each other. At the end of the day, did students who take a mindfulness class perform better on their verbal GREs compared to the students who took the nutrition class? Okay, so looking back here at a post-test only design, there's only one comparison that we can make, right? And it's right here. I don't know if you can see my cursor moving up and down, but what we would be looking to see is, did the students who were part of this group, this treatment group, perform differently or better compared to students who are in this treatment group? And here we can say, yes, we're comparing these two groups to each other. We can also compare within these groups to see, did they change over time, or did they do better after the fact compared to their baseline score? Okay, so sometimes it's really helpful to have a baseline measure to know how much people improved due to whatever treatment you gave them. All right, so these are both types of between-person experimental designs. Getting into within groups designs or within person designs, there's two ways that we can do this, either through repeated measures or through concurrent designs. So repeated measure designs are when, just like it sounds, we're going to measure participants more than once. All right, so everybody is going to be part of the same group. In this example, we're going to have people taste different chocolates and rate their opinions of that chocolate. And there are two different conditions that they're going to be exposed to. So we can tell the independent variables here by the red boxes, okay, and the dependent variables are in the blue boxes. So we don't need to worry about random assignment because everybody is part of the same group. Everybody is first going to be exposed to this condition where they taste chocolate with a confederate. So with somebody else in the room, maybe a researcher who's maybe telling them something about this chocolate. Okay, I actually don't remember what your book actually says about this experiment. I think I wrote it at the bottom of the slide though, so you can take a look there to refer to the details. But basically all we need to know is that this is the first condition, that people tasted chocolate with a confederate in the room, and then they rated that chocolate. Okay, and the next condition, this same group of people tasted chocolate alone, and then they rated the chocolate after they tasted it. Okay, so what the researchers might be trying to determine here is whether or not the rating between these two times for the same participants were different according to the condition. Did they taste the chocolate alone, or did they taste the chocolate with somebody else who was maybe telling them something about it? Okay, hopefully that makes sense. A concurrent design is where all conditions of the independent variable are presented at the same time, and there's a single measure of the dependent variable or the outcome. So we use concurrent designs a lot of times in infants. So some of you may be familiar with this method of determining infant preferences by how long they look at something. So this example here, kind of refers to that we have all the infants in one group. We're going to present two cards to them, maybe, or two screens that have a female face on one and a male face on the other, and we're going to measure their looking preference and maybe how long they look at one or the other. So these are the two conditions here in a concurrent design. They're exposed to both things at the same time, and these are things that are controlled by the researcher. They're determined by the researcher, and then this dependent variable is what's measured, okay, to see what they prefer or how long they look. When I was going through these slides earlier, I thought of another example here. If anyone has ever done this with their dog, I actually haven't, but maybe I should. You give your dog, or you lay out two plates, and on one plate you have a hamburger, and on the other plate you have a piece of fried chicken. Okay, and you hold your dog back, at one end of the room, and then you make bets on what are they going to go for first, and you let the dog go, and you see what they eat. Okay, probably not the healthiest thing to do to your dog, but it's a good example of a concurrent design. So the two conditions there would be the hamburger or the chicken. Okay, your dog would be part of this group. You could maybe do it with multiple dogs. I don't know, maybe that's not a good idea. And then your outcome, your dependent variable, would be the measure of what did the dog choose. Okay, hopefully that'll help you guys remember that. Within group designs, there are some advantages of within group designs over between group designs. It's not as easy to do. You need to have a large group of people, and it takes a longer period of time because you have to measure people, multiple times through these different conditions. However, there can be advantages. Participants in your groups are the same people, okay? So they're serving as their own controls. Rather than comparing these measured outcomes to different people or, making comparisons between different people, you're actually comparing the same people and how they performed in one condition versus another. So it can be helpful to have that kind of baseline and knowing that these are the same people and there's no, additional maybe underlying confounds or systematic differences that you're not aware of. They can require fewer participants than other designs, so if that's an issue, it can be helpful to have the same people just participate in each group, although it can take longer. And then it can also give researchers more power to detect these differences between conditions because you have more certainty about the baseline and about the fact that you're not comparing between different groups of people. Okay, so we've made it this far. That's all that I had to cover on experimental designs. Again, there's a lot more detail that we could get into. What you should know for the final is, the terminology that we discussed, and have an idea of how these different types of experimental designs could work or could be applied. Okay, so have a sense of what goes into a pre-test, post-test design versus a post-test only design and how they may be useful. So this last part, or the second part of today's slides that I'm going to go over, are longitudinal designs. Okay, and this is relatively a lot shorter, but it's still really important. So longitudinal designs, we're going to talk about cross-sectional and actual longitudinal designs, you can actually gain some sense of change over time from a cross-sectional or a cohort design, which is why I'm discussing it here. So a cross-sectional design is when you have two variables that are being measured at the same point in time. Okay, so many studies that we read about are cross-sectional, that everything is happening at the same time, and we're looking at that one point in time and how things are associated. To turn this into something that resembles a longitudinal design, we can look at cohort differences or cohort effects. Cohort effects can actually be problematic, okay? So I shouldn't refer to that as something that we want to do ideally. But sometimes we do make comparisons between people who are part of different cohorts, who are different ages at one point in time, and who are studied to reflect that. Okay, so a cross-sectional design might look like, today I collect a sample of people, and I have, a quarter of my sample is in their 20s, a quarter is in their 30s, a quarter in their 40s, and so on, a quarter in their 50s. All right, so my sample is broken up by different ages. If I want to make an assumption or, test a question about differences according to those ages, I could have a problem that relates to the cohort that those people are part of. Okay, so today they're actually a part of a different generation. They may have different societal conditions rather than developmental conditions that affect how they perform in my study. All right, so a cross-sectional design, I've broken this down, what I just explained, into a table here. You would maybe get a sample of people who were 30, 40, 50, and 60, who were born at these different periods of time. All right, what we're going to be able to say about these people in a sense of their development is really kind of limited based on these cohort effects. Okay, what somebody is experiencing in 2015 as a 60-year-old is probably pretty different compared to somebody who was 30 in 2015 and who was born in 1985. Okay, so they have different kind of generational experiences based on their cohort that are going to affect our interpretation of development. A longitudinal design where we are tracking people who are born at the same point in time and who are growing older at the same rate, obviously, is a much better way to understand development. Okay, this is also not as easy to do. So a lot of times we do see cross-sectional designs where we're making these comparisons between people who are different ages right now. But it's much better to do a longitudinal design in this way, where we track people who were born in 1990, who were 5 in 1995, 10 in 2000, and so on. Okay, so this allows us to have a baseline that everybody who is a part of our study is developing at the same point in time. Okay, so everybody is 5 in the same year. We don't really have to worry about generational effects being a problem or interfering with the data that we collect or our interpretation. We also can have individuals serving as their own baseline or as their own control. Like I mentioned in some of those experimental designs, this is ideal. When you know what somebody was like 5 years ago and you can control for that, you're much less likely to have bias in your interpretation going forward and making assumptions and trying to understand, this course of development for individuals. It's much better to be able to compare people to themselves than to other people, right? A potential problem with a longitudinal design like this is obviously dropout. Okay, attrition is a big threat to the internal validity of a longitudinal design like this. We talked about this last week, that attrition can be a problem, especially when it is systematic. But pretty much all longitudinal studies have to deal with some form of people dropping out. When we are making sense of the findings that we get from a longitudinal design, typically we are going to look at correlations how closely related are variables over these time points. Okay, so this is a really simple way of determining development. Okay, so autocorrelations are just telling us between time 1 and time 2, so overvaluation, this is a personality trait. Between time 1 and time 2, somebody's level of overvaluation, or I should say the sample level, was correlated at almost 0.7. Okay, so almost 70% of what they reported at time 2 was dependent on what they reported at time 1. Okay, same thing between time 2 and time 3, that correlation is 0.6. Okay, time 3 and 4, you can look there too. So these are pretty high correlations, which would be expected that when we're looking at the development of a personality trait, which is, tends to be relatively stable, how does that change over time? The correlations are pretty high. We can also look at cross-lag correlations where we are trying to understand the associations between these two different variables relative to one another and how they influence each other over time. Okay, so I'm actually doing a study using a cross-lagged analysis right now. I mentioned this study of co-parenting and adolescent adjustment, right? So it's the same study where I am trying to understand whether it's co-parenting problems that predict later adolescent adjustment problems, or if it's the other way around, that earlier adolescent adjustment problems predict later co-parenting conflict. Okay, and what I'm actually finding is that it's the adolescent adjustment problems when adolescents are taking more risks, when they have higher levels of anxiety or depressive symptoms. Those kinds of things can actually negatively interfere with the co-parenting relationship and bring about more conflict rather than the other way around. Okay, so it helps us to understand at this time point, pretend that this says adolescent adjustment is relating directly to co-parenting, the second variable at time 2. Okay, and we don't really see so much of a pathway from co-parenting at time 1 to later adjustment problems at time 2. Okay, and you can just kind of extrapolate this out over time. There are 4 time points in this study, and you can see the same pattern of association through these cross-lag correlations, that it's really variable 1 that's affecting variable 2 later on. Okay, and not so much, these are all, NS means non-significant, these pathways are not really significant, they're not showing much. Okay, so this is a way to measure longitudinally between different variables. It's also a really good way to establish temporal precedence. Okay, this shows us very clearly which variable came first in time and what the direction of the association is. So even though it's a correlation, we have the sense of what happened first. All right, so last slide. Thinking about longitudinal designs and the 3 causal criteria. So longitudinal designs can definitely help, okay? Again, they don't always get to internal validity. They don't always help us resolve or, completely establish internal validity, but they can provide some evidence for causation by fulfilling covariance or association and temporal precedence. Okay, longitudinal designs are considered the gold standard to some extent in our field. Again, there's not a lot of room for experiments all the time. We don't do a whole lot of experiments. We can do a lot of longitudinal studies. It's really relevant to development, and it helps us gain some insight into what happened first and how can we understand that to predict future outcomes, okay, which can be really useful. So longitudinal designs, in some can help us to establish those first 2 criteria, covariance and temporal precedence. It's a little bit harder to establish internal validity, as it is with most studies, to eliminate all of those third explanations. Okay, that's the end of these slides. So hopefully this was useful for you guys. Again, if there's any questions about any of this, please feel free to reach out and contact me. I also, I know I'm a little late getting these posted, so if you need some extra time to complete the assignment and the quiz, it's no problem. I can give you, a couple of extra days to work on that, so just let me know. Okay? I hope everybody has a good weekend and everybody is still staying safe and healthy. I made a note on Blackboard that I'm not going to be available on Monday morning. I have a faculty meeting during that time, so there will be no live session this week. Next week, or I shouldn't say this week, I should say this coming week. No live session on May 4th. However, our last day of scheduled class, May 11th, we will have a live session at 10 o'clock, and that will also serve as a review. Okay, so that'll be the day that I post the final exam for you to start working on, so we'll have an opportunity to discuss any questions that you might have then. Okay, so I will talk to all of you guys soon. Have a good weekend.